Okay, so now that Unit 1 and Test 1 are behind us, we can start our new material. This unit also goes a little bit quickly, so we'll stay on top of it here. Just wanted to try to peek quick at when Test 2 was for you, so you have a heads up on that. Test 2 is... what chapters are we covering? Test 2 will cover chapters 3, 4, and 5. So right now we're going to be talking mostly on chapter 3.
Okay, so that's what's in Unit 2 is 3, 4, and 5?
Correct.
Thank you.
You bet. So anyway, yeah, June 30th in class will be our Test 2. So that'll be 2 weeks from this Thursday, I believe. June 30th. Yep. Yeah, that'll be 2 weeks from Thursday. If you're going to be gone, just let me know and we'll make arrangements to make it up. 1 week from this Thursday, I'm sorry. Did I say 2? Yeah. 1 week from this Thursday, I'm sorry.
I was like, wait.
Yeah, so like 9 days from today. So we have today's class, then we have 2 more full lectures. 3 more full lectures, and then we'll test. So about the same length as Unit 1. Okay, so we want to look at a little bit of geometry concepts today. We're going to start out with probably the most basic concepts in geometry. And there are, well, the basic concept in geometry that everything is built off is this concept right here. It's a location, and it's referred to as a point. And that's literally all it does is it marks a location. Now another concept we have is the concept of a plane. A plane is just a flat surface. Now technically a plane goes on forever in every direction. And the reason it's such an important concept is because most of what we do is on a piece of paper, which is a form of a plane. Next, everything in geometry is built upon that basic point and a movement. And so we're going to look at moving that point. And one of the ways we move that point can be described as, of course, directions is going to be important. We'll discuss that more in a little bit. And then there's something called the concept of perpendicular. How many of you are familiar with the term right angle? Sure, most of you? A right angle is just basically a square corner. Perpendicular is kind of a souped up version of that. It's a more complex version of a right angle. Perpendicular means two things are perpendicular if they form right angles with each other no matter how you measure it. For example, we talked about a plane. So picture this as being a flat surface. A line is perpendicular to that plane. So let's say I draw this line through there. If, no matter what direction I measure the angle between that line and the plane, it forms a right angle. So no matter what direction I'm going in, it's at a right angle to that plane. That's what perpendicular means. Okay, so now let's start with this idea of direction here. The original idea of direction, this is kind of outdated and we don't use it a whole lot anymore, dates back to navigation. And in navigation, you had a 0 degree direction, which is usually, if you're looking at the compass, would be the east direction. Then you had the 90 degree direction, which was north. 180 degrees would be west. 270 would be south. And then 360 would be back to east, a full circle. So technically you don't really reach 360 degrees, you get reset back to 0. And then, of course, if we have an arrow pointing like this, its direction is obviously between 0 and 90, and whatever portion of the way between there gives us what that direction is. That one looks like it might be, let's just say it's at 29 degrees is its location, its direction. That's going to be important to us when we look at some of our other constructions in geometry. So anyway, let's look at some of our basic things that we are going to construct. So we're starting with that point. We can take that point, and remember we said it was all about movement. We take that point and we move it in a single direction. What we have created here is technically what we call a line segment. A line would go on forever in both directions. In the real world, a line does not have a whole lot of use. A line segment is what we typically use. And in a lot of cases, when you hear the word line, what they're really talking about is a line segment. Now, the length of that line segment is equal to the distance that that point was moved. Which makes sense, right? If you move it a certain distance, you create a segment that long. Just like taking a stick and dragging it across the sand. The distance you pull the stick is how long the line is. You create the line segment as you create the sand. Now I can continue with that concept. If I take a point and I pull it in a single direction and I keep on going forever with it, I've created a ray. You think of this as like a ray of light, a ray of sunshine. It starts at the sun, but then it goes out and it keeps on going forever. And of course, a ray has that starting point and it has a direction. I've been drawing all of these relatively horizontally. This one's not quite due east or 0 degrees, but close to it. So now those rays are used to form one of our first geometric constructions that we're going to be working with. If I take that point and I move it in that single direction, I created a ray. Now I'm going to label that point as point A. Out here somewhere, this ray goes through point B. So I would name that ray AB. That little arrow is the abbreviation for a ray. Now if it was just a line segment, let's say it was just like this, from point A to B, that would be labeled as segment AB. Now it could also be labeled segment BA. A segment has no set direction once it's been created. For a ray, however, you must name the starting point first and then the other point that it goes through as it's traveling. So it does always have that arrow on the end for a ray that tells you what direction it's going. So now let's say I go back to point A and I'm going to pull it in a different direction. This time we're going to go through point C. So I've created now ray AC, starting at point A and going through point C and continuing on. These two rays that share a common starting point that common starting point is referred to as a vertex. So these two rays that share that common starting point or share that vertex form what we call an angle. Now most of you have probably seen angles and maybe even measured angles before. Technically, the size of an angle was defined by a difference in direction. So let's say a ray AB here is at 23 degrees. And ray AC is at 54 degrees. The angle that they form here is the difference between that. 54 minus 23 is 31 degrees. So this would be referred to as a 31-degree angle, the difference in the directions. Now, not many people do navigation anymore. This directional system is still used in surveying, and that's, airplane navigation, nautical navigation, and stuff like that. But it's not as common for for everyday people to know that as they used to. So we've adjusted our definition of an angle. We still get the same angle. This is going to be 31 degrees no matter how we measure it or define it. But we've started to look at it like this. Let's say I start here and I rotate in a complete circle. How far have I rotated? 360 degrees. Very good. Let's say I start here and I rotate so that I am moving in exactly the opposite direction. How far have I rotated? 180. That is defined to be 180 because it is half of the 360 degree turn. So let's say I start here and I rotate so that I have formed a square corner here. That little box that you see when you make a right angle, by the way, is a square, and it's there to show that that's a square corner. The square fits in that corner. How many degrees would that be? 90 degrees. And it's 90 degrees because it's 1/4 of a full turn, a 360 degree turn. And so that is kind of the new definition of an angle. Is a fraction or portion of a full turn of 360 degrees. For this class, we're not going to be using protractors and actually measuring the angles. We're just going to be working with the numbers once we're given the angles. Now, once we have the angles, there are some relationships that we can deal with. For example, I'm going to create this angle here. Now, my vertex I'm going to label point M. I'm going to put point P and point N here. Now, this angle is made up of two rays. Ray, what's one of the rays? MP. Could I have called it PM? No. For a ray, you have to have the starting point and then the other point that it goes through. For a ray, it does matter what order it's in. For a segment, it does not. What's my other ray named? MN. Very good. Again, you have to name the starting point and then the other point that it goes through. And these two rays form an angle. And to name an angle, I use this symbol, which is the angle symbol. I name the point on one side. So I'm either going to go with P or N. The middle letter has to be the vertex, which is the M. And then I have to name the other side. So this angle could be called angle PMN, or it could be called angle NMP. Name one side, the vertex, and then the other side. Now, a little bit variation of that symbol looks like this. This little M in front of the angle symbol stands for the word measure. Measure means how big is it? So let's say that this is 27 degrees. So the measure of angle PMN would equal 27 degrees. So this is just referring to the angle itself. This is referring to how big is it? How many degrees is it? You won't be tested directly on that, but in my math lab, you'll see that symbol come up. M angle ABC equals blank. Well, you have to know that. Oh, that's asking you to find the degrees. Okay, so now that we have this angle, we can form a third ray from that vertex, from M, that might go off like this. So we'll call that ray MQ. And let's say here that angle NMQ has a measurement of 41 degrees. If we look at these two angles, angle PMN and angle NMQ, they share a vertex, which is just point M. But they also share a side, which is ray MN. Any two angles that meet those two qualifications, they share a vertex and they share a side, are what we call adjacent angles. The reason adjacent angles are so important is when we have adjacent angles, our algebraic properties apply to them. They're additive, subtractive, and so on. So let's say I wanted to find the measurement of angle PMQ. What that is this angle right here, this whole big one here, finding this measurement. Well, how would I find that measurement? I just do 27 plus 41. Gives me 68 degrees. So this angle here would take on a measurement of 68 degrees. Just adding the other two angles together. So let me call this A, B, C, and D. I'm going to ask you to find the measurement of angle A, B, D. Tell me how I would do that. You got it. 79 degrees?
79 and
Yep.
the 43.
Perfect. We're going to add the 79 degrees and the 43 degrees to get the overall angle. To get 122 degrees. Now a slight variation of that, the same concept, would look like this. Now, when I do this with two little arcs in there instead of one, all that is showing me that the two of them are not equal, that they're different sizes. So here, I am given that the measurement of angle HIP equals 79 degrees. I am given that the measurement of angle HIM equals 51 degrees. So what I want to find is the measurement of angle MIP. How am I going to find that one? Exactly, we're going to subtract. If I call this x, we know that x plus 51, or 51 plus x, has to add up to 79. One of our basic equation types from before. So to find x, we would just subtract the 51. Now, most of you wouldn't write out the equation. You'd probably just do 79 degrees minus 51 degrees, which will give you 28 degrees. Any questions so far? Okay. So now our adjacent angles have some special relationships. One of those potential special relationships would look like this. So let's say I have T, U, V, and S. Here, angle TUV, the measurement of angle TUV plus the measurement of angle SUV has to add up to what? Well, this across here is a straight line. And how many degrees is a straight line? 180. Very good. So we know those add up to 180 degrees. When two angles combine to make a straight line, it's what we call supplementary angles. So now if I fill in one of them, let's say I tell you that this one here is 112 degrees. What's this angle? If SUV is 112, TUV must be 180 minus 112, or 68 degrees. Perfect. Now, if two angles that combine to make a straight line is one special relationship, you might guess that the next special relationship might be two angles that combine to make a square corner or a right angle. So let's call this MOP R. So here, what do we know about the measurement of angle MOP plus the measurement of angle POR? What do they have to add up to? This one. What is it? 90. Perfect. They add up to a right angle. They combine to make a right angle. So that's 90 degrees. Two angles that add up to 90 degrees are what we call complementary. So here, if I happen to know that angle MOP is 31 degrees, how do I find angle POR? Subtract. Good. 90 degrees minus 31 degrees is 59 degrees. Now, if you're anything like me, I've never had a problem remembering the words supplementary and complementary. What I've had a problem with is remembering which one is which. So I think of it this way. Complementary angles add up to a right angle. And your teacher compliments you when you are right. That's the only way I've ever been able to remember the difference between them. Yes?
Supplementary angles are only 180 degrees or angle?
Supplementary angles add to 180 degrees. Only adding to 180 degrees, yes. They must add up to exactly a straight line. And then the same with complementary angles. They will add to exactly 90 degrees. Now, looking at this example here, you can see, of course, that this is a straight line across here. And you could probably calculate x pretty easily. But what we want to practice doing is writing equations for these geometric situations. Because as the variables and the expressions get more complex, we're going to need the equations to find them. So for something like this, if I'm asked to find x, how would I write the relationship that describes these two angles? Well, what is their special relationship? They're supplementary, which means they add to 180 degrees. So x plus 76 equals 180. Now we have an equation that we can quickly solve to find x. Of course, we would subtract 76. that x equals 104 degrees. And now I realize most of you could look at that and say, oh, 180 minus 76 and get the 104. You wouldn't have to write the equation. But again, at some point we're going to get to situations that you need the equation to figure them out. Just to give you a little foreshadowing, they might look something like this. I can't look at that and just simply add or subtract to find what x is. I want to find both angles here. What is my relationship between the two angles? They're still supplementary, which means they add to 180. So 2x plus 4x has to add up to 180. Now I'm going to pause there. Any questions on where this equation came from? We're just adding the two measurements to get 180 degrees. Now what can we do to solve that equation? Well, we can combine. Perfect. Yeah, the x appears twice, but they're both on the same side of the equation. So we can just combine them into one big pile of x's. 2x and 4x make 6x. So 6x equals 180. And then we solve it by division, dividing by 6. X equals 30. Now we have to resist the temptation to stop here. We've written an equation, we've solved it, we got the value of x. We feel like we should be done. But what are we asked to find? Find both angles. We have not done that yet. All we've done is found the value of x. So we have to make sure, once we've solved our equation, we go back, look at the question again, and make sure we've actually answered the question. So this angle is 2x. That's 2 times 30, which is 60 degrees. This one is 4x. So 4 times 30, which is 120 degrees. Now I can double check. Do they add up to 180? Yes, they do. So they make sense. So looking at these two angles, how would I express the relationship between them? Well, they are complementary, which means they add to 90 degrees. So y plus 19 has to add up to 90. And again, quickly solving, what would we do? Subtract. Perfect. Subtract 19 gives us that y is 71. So 71 degrees. Now again, most of you could just look at that and say, oh, that's got to be 90 minus 19. But we're going to run into situations that are a little bit more complex. Like, of course it has to get worse, right? And again, I want to say find both angles. What's this relationship going to be? Yep, it's complementary again. So I'm going to write, go ahead. So they add up to 90 degrees. So what am I going to write for my equation? 7x plus 11x equals 90 degrees, equals 90. Now what do I do to solve this? Combine them. 7x and 11x is 18x equals 90. And then divide by 18, x equals 5. Now again, we're not done. We still have to answer the question. We have to find each angles. This angle is 7x. So 7 times 5 is 35. That's 35 degrees. This angle is 11x. So 11 times 5 is 55. So that's 55 degrees. And again, we can double check. Do they add to 90? They sure do. So that is the correct answer. So I have two lines that intersect here. Now they're not perpendicular, because if they're perpendicular, they'd have to form a right angle or a 90-degree angle in every direction. So they're not perpendicular. If I give you that this angle right here is 37 degrees, how can I find this angle right here? I'll call it x. Well, there's two ways of looking at this. One is you could think it in terms of rotating. If you look at if I have two lines, let me use a couple of pens here. I have my black line and my red line. If I have them on top of each other, and I'm thinking of forming angles by rotation, as I rotate the red line, the amount it rotates here is the same as it rotates on the other side. Okay, so much for my visual aids. Anyway, another way you could look at it is in terms of what we just discussed. Our adjacent angles and their relationships. If I look at this line here, and I look at the 37 degrees and this angle, I'll call it angle Y. What's the relationship between them? Yeah, supplementary. They make a straight line. They're supplementary. They have to add to 180. So I can find Y by taking 180 minus 37, which is 143 degrees. Well, now let's look at this line. If I'm looking at that line, what's the relationship between Y and X? They're supplementary, which means they have to add to 180 degrees. So I can find X by taking 180 and subtracting Y, which is 143. That'll give me 37 degrees. When I have two lines that intersect like this, these two angles that are formed on the opposite sides of the intersection are what we call vertical angles, corresponding if you do parallel lines. They're called vertical angles. So those angles are always equal. They have to be equal because this angle is supplementary to this one. This angle is supplementary to this one. Well, if you're adding the same thing to each of them to get 180 degrees, you must be starting with the same thing. So let's say that this angle here is 3x minus 11. This angle here is 2x plus, let's call it 13. I ask you to find each angle. What's the relationship between those two angles? Careful. They're vertical, which means they have to be equal, the same. So far, everything we've looked at has been two things adding up to make a total. This one's actually a little bit simpler, at least initially. What we know about these is that the 2x plus 13 angle has to equal the 3x minus 11 angle. That's always the first step when dealing with geometry, is figuring out what relationship it is that we actually have, that we're dealing with. Now to solve this, the x appears twice. but this time it's once on each side of the equation. Think of that balanced scale. The 2x and the 3x are on opposite sides. That means I can't just push them together and combine them. I have to get rid of one of them. And I usually try to get rid of the smaller one so that I don't have to deal with negatives. Which one am I going to get rid of here? 2x. It's a positive 2x, so to get rid of it, I subtract. Now, I sometimes get asked, why don't I just divide by 2? Well, dividing by 2, 2x, if you divide it by 2, cuts it in half. What's half of 2x? 1x, so it's still there. I want to get rid of the x completely. I don't want to get it just down to x. I want to get rid of the whole thing. So the only way to do that is to take it off or to subtract. So that's gone. Leaves me with 13 over here. But I have to do exactly the same thing to the other side. So I have to take away 2x there. Can't take it from the negative 11 because it's a different name. The only place I can take it from is from the 3x. What is 3x minus 2x? It's 1x, or we can just call it x, right? We don't have to write the 1. We still have the negative 11. So 13 equals x minus 11. What do we do next? It's a negative 11, so we have to add 11. You had the right idea. Good. So add 11 to get rid of it. 13 plus 11 is 24. X equals 24. Once again, we still have not answered our question. We have to find each angle. So we come back here. 2x plus 13 becomes 2 times 24 plus 13. And now it's order of operations. What do we do first? Multiply. 2 times 24 is 48. Then we add 13 to get 61. 61 degrees. Now over here, are we looking for this to be adding up to 180 or 90, or what are we looking for? This one better come out to be 61. Let's double check that. So 3 times x is 24 still, minus 11. What do we do first? 3 times 24 is 72. Minus 11 is 61, which is what we needed it to be. So each of those angles is 61 degrees. Any questions? All right. So that is the first part, is always to figure out what is the relationship. Do they add up to something? Do they equal each other? Or how do we have to go about that? Now I should note, by the way, as you can tell here, none of my drawings are ever done to scale because that is nowhere near 61 degrees in reality. Okay. Other geometric relationships. We created that length by taking that point and moving it in a single direction. We created that length. Now, if I take that line segment and I move the whole segment in a second direction. So I'm just going to trace over it here, and I'm going to move it in a second direction. But the key is that second direction has to be perpendicular to the first. Think of that dragging a stick across the sand again. What it traces out in a sand is this thing called a rectangle. So the original length that we move the point is the length. The distance we move that whole line segment is often called the width. Some things we can do with that rectangle, one that we've already discussed in the last unit a little bit for problem solving, is perimeter. Perimeter is found by, well, the technical definition of perimeter is distance around. Now remember, distance is measured by movement. So that'd be the length plus the width plus the length plus the width. In the last unit, we looked at simplifying that formula. What can we combine there? L and L. Yeah, we think of this as 1L and 1L make 2L. 1W and 1W make 2W. Perimeter is equal to 2L plus 2W. So if I give you a simple rectangle, and I tell you that the perimeter equals 24, can I find L? Sure can. P equals 2L plus 2W. What do I know? Do I know P? Yeah, 24. Do I know L? No. Do I know W? Yes, it's 5. And now it's just a matter of solving that equation again. What do I do first? We'll combine the 2 times 5. So that's just 10. And now I can go ahead and solve the equation. I've simplified everything I can. So I would have to subtract 10. 14 equals 2L. And then divide by 2. So 7 equals L. And that actually is what I was looking for there, was just the length. So let's go back to this line segment again. We said the length of that line segment is equal to the distance we moved the point. Well, the width of that rectangle, if I take that segment and I move it in a second direction, the width of that rectangle is also equal to a distance. It's the distance I moved that line segment sideways. Label my width and length again. So the area, which is the amount of space covered by that rectangle, depends on 2 things. It depends on how big that original length was, and then how far we pulled that length sideways, what the width is. So area is defined usually as a length times a width. Now later on in the summer, when we look at areas and volumes in more detail, we're going to look at a more universal way. This length times width only really applies to rectangles. So we're going to look at a more universal way, a more useful way of finding areas. It applies to just about anything you want to find. But for right now, this is our simple formula. So if I give you a rectangle that has a length of 12 inches and tell you it has an area of 60 square inches, can I find the width? I sure can. What am I going to put in here for area? 60. I know that L is 12, and I'm looking for W. This equation is a relatively simple one to solve. What do I have to do? Divide by 12. 5 equals W. Any questions? Now, volume can be thought of as taking that rectangle now. Pretend this is a rectangle. I know it looks like it's slanted, but it really isn't. It's a perspective. If you're looking at it from above and slightly off to the side. If I take that rectangle and I lift it up, so what I'm really doing is I'm moving it now in a third direction that is perpendicular to each of the first 2. If I think of this as being my first direction, this was perpendicular when I moved it that way to make the rectangle. Well, this is also perpendicular when I lift it up to make this box. The volume of that box depends on how big that area was and this distance, which we call a height, that I moved that area. When we come back to doing areas and volumes more universally, this is the definition of volume we're going to use. For right now, though, we can use a definition of volume that applies just to boxes. How do you find the area of that rectangle at the bottom? Length times width, right? So that area is just length times width times the height to get the volume. So let's say a box containing, oh, let's make this reasonable here, 400 cubic inches is 4 inches wide and 10 inches long. Find the height. Well, we've got our formula. Volume equals length times width times height. Do we know the volume in this situation? 400. You got it. Do we know the length? 10. Times, do we know the width? 4. Times, do we know h? No, there's got to be something missing, right? We've got to be looking for something. So I have that equation. 400 equals 10 times 4 times h. What do I have to do first? Combine the 10 times 4. 10 times 4 is 40. So that's 40 times h, or 40h. And then divide by 40 to get h by itself. So 400 divided by 40 is 10 equals h. My height is 10, and you probably should put the units on that. Everything's measured in inches here, so that would be 10 inches. Any questions? Okay. Not everything's going to stay quite that simple. You're going to have some shapes that are maybe a little more complex. We'll start out with something like this. Assume at this point that all of my corners are square corners. Let's say this is 20 feet and this is 36 feet. This is 12 feet here, and this is 22 feet here. Let's find the perimeter. Well, this is not a simple rectangle, so the only way we can find the perimeter is to add up the sides. So let's pick a side to start with. Let's start right here. So the perimeter is going to be 36 plus, so go around, that's 20 plus, what's next? We got to find the length of this side, don't we? How long? Well, we can call it x. Can we find out how long x is? Perfect. If we're looking at this, we know that this length here has to be equal to this one plus that one. Anybody that doesn't see why those two have to add up? Because to get from here to here has to be the same whether we're measuring it on top or the bottom. So what we have there is that x plus 22 has to equal 36. But of course, to find x, you're just subtracting the 22, which means x is 14. So you're going to put 14 in here. What's the next side? 12 plus 22 plus, let's call this one y. How do I find out how long y is? Very good. We know that 20 here has to equal y plus 12. Because again, this is the height of the figure, or I could add up these two to get the height of the figure. So I would subtract 12 from 20 to get that y has to be 8. So I'm going to add 8 there. If I add those all up, that should add up to 112 feet. Now, there's a couple of things here. I'm going to start with the easier one. Does everybody see why we're adding up these numbers to get the perimeter? Any questions on where those numbers, why we're adding those numbers? Because we are just adding up, we're picking a starting point, which is right here. We're just going around adding up the sides as we go until we get back to that same starting point. That's our perimeter. You can think of the perimeter as how far would you walk if you actually walked around the outside edge. Just add up the sides. Now the second big question, and usually the one that has more questions, is anybody have questions on how we got the 8 for y and the 14 for x? That's one that in the last 7 or 8 years has become a real struggle for a lot of students, is finding those missing dimensions. Pardon me? Yep.
And for y, we were at the 20 from the 17.
Oh, 12 from the 20, yes. Yeah, I've got, my line goes through that, so it looks like 17, but it's 20.
Yeah.
Okay. So yeah, you just have to look at, if you have, and one of the keys is, y here is a vertical dimension. So to find out how long it is, you have to look at the other vertical dimensions, the other up and down pieces. X is a horizontal dimension, so to find it, you have to look at the other horizontal or side-to-side pieces. But again, if that is something you have questions on or struggling with, please ask, because that is one of the concepts that in the last 7 or 8 years students have struggled with the most, is finding those missing pieces. Okay, well, same picture, same dimensions. What if I ask you to find the area? Well, the area, we only know how to find the area of a rectangle. This is not a rectangle. But we can make it into rectangles by cutting it. I could cut it that way, or I could have cut it here. It doesn't matter. Either one turns it into rectangles. I'm going to cut it this way. So what we have now is 2 rectangles, rectangle 1 and rectangle 2. What are the dimensions of rectangle 1? Well, this is 20 feet times, we need this dimension, we found it before, it was 36 minus 22 is 14 feet. So that area is 20 times 14, or 280 square feet. Now for rectangle 2, we know this dimension is 22 feet by, what's this dimension? We found that one before too. That one's going to be 20 minus 12, which is 8 feet. So 22 times 8 is 176 square feet. So the area of this whole thing is found by adding those together to get 456 square feet. Any questions? Well, I think I've done enough damage for the day. So, there will be no quiz today. That's your reward for taking the test today. But there is a new homework. That will be due Thursday. Remember again, by the way, New Richmond campus will be shut down on Thursday, so you have the option of either coming to Rice Lake or going to Superior or waiting and viewing the recordings later in the day. I will make a point on Thursday to make sure the recordings are up and posted by 2 o'clock in the afternoon.